Hi everyone, that's Mohammed again, and I'm continuing the series of updates that I'm making for my YouTube videos, and this time it's going to be the I2c video. So in today's tutorial I'm going to show you how to use I2c with the STM32F4 Discovery board with and without CubeMX. So in the first 6 and 7 minutes I'll show you how to do that with CubeMX, and towards the end of the video I'll show you how to set everything up from scratch without the help of CubeMX. So the second part is mainly for people who want to learn more about low-level programming of the STM board, and that's ideally students. Okay, and just a very brief introduction before we make start. I2c is a two-line serial interface. It has got a clock line and a data line, and you connect the slaves in parallel, and each slave must have a unique slave address. And in my demo today I'm going to use a single slave device, and that's going to be the accelerometer sensor. This one has got accelerometer, gyroscope and magnetometer on board. We only going to use the accelerometer in today's demo. This is an I2c based sensor that I'm going to connect in my demo today. Okay, so let's get started with CubeMX. So open CubeMX and click on New Project and select the right board. By the way, this is the updated CubeMX version. So the series is F4 and the line is 07, and it's 100 pins package, and it's VGT, so that's the one. And now on the pinout, first we need to enable I2c line. I'm going to use I2c1 here. So click on this and select I2c. And you'll see two lines being enabled. So it's BB6 serial clock and BB7 is the data line. I'm also going to enable a single LED. And that's it for the pinout. And we're not going to change anything on the configuration. We'll leave everything as default. So we're ready to generate the source code. So click on this icon. And give the project a name. I'm going to call it I2c video. Store it at this location and select the right IDE. Keil Macrovision 5 in my case, and click OK. And now hit Open Project, and this will take you to your IDE. Okay, on Keil Macrovision, expand this folder, Application User, and open the main. And the first thing I want to do here is that I want to scan for the I2c addresses. I don't know what the I2c address is. So I'm going to do this manually. I'm going to scan for the addresses. So we're going to do this in a for loop. So we're going to scan the I2c addresses from I equal to 0 to I equal to 255. So we're going to scan the whole 8 bits addresses. And there's a function in the HAL library called sDeviceReady. So we're going to use this to test for the slave address. So that's the function. The function takes a few parameters. The first one is the I2c handle type diff, then the address, so it's I, so I'm scanning the whole addresses from 0 to 255. The trials, just want to try one time. The timeout is 10 milliseconds, and if this one is equal to HAL OK, then I'll break the loop and look for the I value. So I need to put an if condition here. And when this one is true, I want to toggle an LED perhaps. So I'll toggle my green LED and we'll break the loop. And then in debugging mode, we will watch the I value. Whatever I value will end up with here, that will be the slave address. So let's compile the code. Alright, my code compiled successfully without any errors. Now I'm going to connect the accelerometer device. So I need to connect VCC 3 volt, ground to ground, serial clock to BB6, SDA to BB7. I know you not necessarily have this slave device with you, but it's going to be similar concept whatever I2c slave device you have. So let's load it to the board and get into debugging mode. And on here, first I want to add a variable I to my watch memory. Okay, I want to watch the value, so I'm going to run up to this line. When this one gets into the if condition, I want to see what the I value is, and that will be my I2c slave device address. So let me run it up to here. Wow, great. It jumped in inside the condition and it's 0xD0. This is actually just like what's described in the datasheet. Okay, so now we got the address. Let's get back to our code, and I'm going to show you how to write and read via I2c. Okay, so first I'll define my slave address just like how I found it in debugging mode. So it's 0xD0. And now I'm going to show you how to write to an I2c device. So I'm going to write to register number 28 to set the accelerometer range. So we need to define an I2c buffer above here so that we use it with the transmit and receive functions. So I call it I2c buffer, size of 8, because at a later stage we're going to read 6 bytes at a time. That's why I gave it size 8. But ideally it will be only size 2 for the register address and for the return data. So an I2c write operation, we first set the register address. So an index 0 is the register address, so it's 28. And on the second byte, the data we want to send via I2c, or the data we want to write to that register. And I want to write 0x08. So here we go. And then to transmit the I2c data, we use a function, HAL library function called HAL I2c master transmit, this one. And the first parameter this one takes is the I2c handle type diff, and a pointer to that, so hi2c1. Then the slave address, which is just what we defined above. We call it MPU9265 address. And then the data buffer and the number of bytes we're sending. So we're sending 2 bytes, the register address followed by the data, and then a timeout. I'm just going to put a timeout of 10 milliseconds. Okay, and this should write to register number 28 the data 0x08 to set the range to plus minus 8G. Just like what's described in the data sheet. So register number 28, if we written 1 to here, we set the full scale or the range to plus minus 8G. Okay, now let's do an I2c read operation. And I'm going to read from the same register, register number 28, just to see that if the data 0x08 has been written successfully. So what we've got to do is that we've got to transmit the register address in its own first, using the same transmit function, so only the register address, which is just 1 byte, and then followed by a read request. And we do this with I2c master read function, receive function. And this one takes similar parameters to the transmit function, so the I2c handle type diff first, and then the slave address, so MPU, and then the data buffer that we want to read to. So I want to read this and store it in index number 1 of the array, and I'm reading only 1 byte from that register and a timeout of 10 milliseconds. I'm going to set this one first to 0 before I do the read operation, and I expect this to be 0x08, just like what I've written initially. And this is how to implement I2c read operation with the STM board. And by the way, this one should be plus or minus 4G. I just made a mistake here, silly mistake. So in the data sheet it says when you write 01, it's plus or minus 4G, and that's what we're doing here. Okay, now we're ready to compile the code, load it to the board, and we'll have a look in debugging mode, and I expect the read data to be 0x08. And on debugging mode, I need to add the I2c buffer to the watch memory, and I'm mainly interested in I2c buffer number 1. So I'm interested in this one. This one changed to 0x08. When I do the read operation, then the write operation was successful, and also the read. So let me run the code straight away. Alright, fantastic. I get 0x08. So I've written 0x08 to register 28, and I read it back successfully. And now we're going to do something a bit more exciting. I'm going to read the X, Y, and Z acceleration data. So if we started with the register 3B and read 6 bytes, we'll end up reading X high and low, Y high and low, and Z high and low. So these are the acceleration raw data, and then we can convert them into G unit of acceleration. So let's do this. So we need to copy the same read operation in here, but we're reading from register 3B to start off with. So same routine, transmitting the register address in its own, followed by read request. But now we're requesting 6 bytes. By the way, I don't need this. I'm reading 6 bytes, starting with position number 1 in the array. And this will give me the raw acceleration data in X, Y, and Z. Each of them has got 2 bytes. But I want to convert them into a G unit of gravity using these formulas, which I need to define the variables at the top. And by the way, I don't expect you to understand all of these formulas, but I'll explain them very briefly. So what these are doing is that the first part, each axis has got 2 bytes. So this one is combining the 2 bytes to make a single 16-bit raw x-axis data. Same for the Y and Z. And this second bit, this one is scaling this properly to convert it to G unit of gravity. So let's give this a go. Let's compile the code, load it to the board, and have a look at debugging mode. Okay, on debugging mode, I first need to add these 3 variables to the watch memory, and let's run the code. Okay, so I'm making my accelerometer device upright, and I should see the G on the Z axis purely, and that's exactly what I see. and I'm going to point the x-axis downward, and I should expect x to tend to 1. That's correct. And now the y downward, and it gets to 1 g of gravity. So this is working. Okay, that's how to use I2c on the STM board with the help of CubeMX. If that's all you're looking for, you may stop the video here, but I'm going to carry on, and I'll show you how to do the same thing without the help of CubeMX. Alright, let's get started. So first go to Project, New Macrovision Project, and select a location to store your project files in. I'm going to store mine in here. I'm going to call it I2c no cube. And now to select the board, STM32F4 VGT. So it's this one, and click OK. And now we need to enable the software components. So the first one is SimSys Core and Device Startup. Go to Cube Framework. And we need to enable the classic one. And this one requires other software components that we can enable automatically by hitting Resolve. And now expand STM32 Cube HAL, and I need to enable the I2c one. This one requires a DMA, so resolve that. And that's all we need on the software components, so click OK. And now Keil Macrovision generated a few files here, mainly the HAL libraries, but it didn't add a main file, so we need to do this ourselves. So right click, add a new item to the group. It's a C file, and we need to call it main. And on our main, we first need to include the HAL library header file, so include STM32F4 HAL.h. And we need to define the main function, so int main, parameter void, and the infinite while loop at the end. And we'll start the main by calling the HAL init function, so HAL initialize. It's called HAL init. You call this one to put everything to their default state. Oh, by the way, I forget something here. I need to put STM32F4XX. So yeah, that's all. And now we need to do two things. We need to configure our GPIO pins and then configure our I2c. So for the GPIO, I need to enable my LED first, and then enable BB6 and PB7 and set them to I2c mode. So I'm going to do this in two separate functions, the GPIO config and I2c config. And for the first function, the GPIO pins function, in here I first need to enable the GPIO ports clock, so port D for my LED and port B for the I2c pins, and then declare a GPIO init type diff. This one is like a structure that we're going to use to set up our pins. And now we will start with the LED pin configurations. So we will use my pin init that we defined, so my pin init dot pin. So I'm only going to enable a single LED, my green LED, so this one is on pin 12 on port D, and the mode to GPIO output push pull, and then some other configurations. So we've got no pull up and the speed too low. Now I can call a HAL init function to implement those initializations. So HAL GPIO init to implement those. So this one will be implemented on port D, and then now I can pass the init type diff in here, a pointer to that. And this will implement those configurations for pin number 12 on port D. And now we'll follow the same procedure to configure our I2c pins. So first we've got to select the pins, and we already know that they're on pin 6 and 7, and then the mode to alternate function open drain. So if you have a GPIO pin, if it's not a digital input, nor digital output, and not analog, then we've got to select alternate function for all the other options. So since this one is an I2c line, so it's on the alternate function multiplexer. An open drain OD means it has got its own external pull-up, and that's what this third line is doing. So it's going to do an external pull-up. So this one is going to implement these two resistor pull-ups on the I2c configuration. And next we're going to set the speed to very high, and after that we set the alternate function to AF number 4, and you can find this in the reference manual. So AF4, the alternate function number 4, and the multiplexer is the one that connects to the I2c ones. And we know PB6 and 7 only connect to I2c number 1, so it's I2c1. And now finally we can call GPIO init function similar to what we did in here to implement those configuration, but this time is on port B, and we pass the init type diff. And just one more thing in here as well, we've got to enable the Systick interrupt. This one is we do this to be able to use the HAL delay function in our main. And if that was very quick for you, don't worry much. I'm going to attach this main.c file down in the description of my video. Okay, now let's define our I2c config function that we declared at the top. And first thing here is to enable the I2c peripheral clock using this function. And then we need to define an I2c handle type diff, similar to what we did with the GPIO. But for this one we need to define it globally, because we're going to refer to it in our main later on. And I call it my I2c handle. And we'll use this one to configure our I2c. So first thing, I need to set the instance to I2c1. And then do some initialization. So the first one, .init. Addressing mode to 7-bit address mode, addressing mode to 7-bit, and then clock speed to 100 kilohertz. This is an ideal I2c speed, and then followed by some other initializations. So we're setting the dual address mode to disabling that, duty cycle to 2, generate call disable, no stretch mode to disable. These are that you don't really need to know more about them. I personally don't know a lot about them. And then the on address to 0. Now we can call in the I2c init function to implement those initialization, and we pass the I2c handle type diff in here. And that's all for this I2c config function. And one very last thing we've got to define as well is the Systick Handler. So this one is usually defined by CubeMX in a separate file. So what this does is that it links the Systick Handler, because the STM system is programmed to jump into this function, not the library function. But this one will match the two together. Okay, now let's scroll up and write our main. So on the main we need to call in the config functions that we defined in here to implement their configurations. So GPI config and I2c config. And now we are on the very same page as the project generated by CubeMX. So now we did all the low-level configurations ourselves. I'm now just going to copy the code I did in CubeMX to here. So what we did in the CubeMX project is that we defined those I2c variables and that I2c accelerometer slave address, and have written these three parts functions to one to scan the I2c addresses, write this one to register 28 and read from 28. And finally the code inside the infinite while loop, the one that reads the accelerometer X, Y and Z data. Okay, so let's first compile the code and see if we're going to get any errors. Superb, there are no errors. Now let's load it to the board. Yeah, I expected that. So now, so STM board has got a stealing debugger, which CubeMX was selecting there automatically, but now we have to do things manually. So go to options for target and go to debug and select stealing debugger. And also go hit on this setting and go to trace and click trace enable, the clock to 60 MHz and click OK. Now it should load successfully to the board. Perfect. And now let's get into debugging mode and convince you that it works the same. And on debugging mode, I'm just going to add the acceleration variables to the watch memory. So right click and add to watch 1. So let's run the code. Alright, perfect. I can see them changing. So when I put my accelerometer device upright, it's the G is only on the Z axis, pointing the X downward, get me on the X axis and the Y downward. And that's how to set up an I2c project on the STM board without the help of CubeMX. And this indeed brings me to the end of my tutorial today. Thanks for watching, and as always, if you found it helpful, don't forget to hit like and subscribe. Thank you, and I'll see you next time.